Okay, now, so let's just make a short review of what we had done on Friday. We had seen that, we were trying to define the potentials in the case of electrodynamics also. And since we know that, well, we basically need to solve 4 equations. So these are the 4 equations we need to solve. Well, if you have a system of coupled equations, at least one of the ways to solving them is that you solve them one by one. Now we can solve the first equation by assuming that B is equal to the curl of some function. So by writing B as the curl of a vector field that we call A, we already solved the first equation. Now one problem was this A is not unique. If A has corresponds to a given B field, so does A plus the gradient of some function lambda. Corresponds to the same B field. So the A is not unique, so to determine a given possible A, we will be imposing some additional constraints on A to be able to choose a single A. Now for this B, written in terms of the curl of some function, we can also solve this equation in a straightforward manner, and it turns out that E is nothing but, we can write it as minus the gradient of some scalar function minus the time derivative of the same A. So this A over here is the A that is defining the B field. But of course, if we change A to A plus the gradient of lambda, electric field changes. We have to make one more transformation, and that is phi goes to phi minus del lambda by del t. So if we change both A and phi, the corresponding electric and magnetic fields do not change. So basically, for a given physical electric and magnetic field, you have infinitely many scalar and vector potentials. And we impose additional constraints on these A and phi to be able to choose one of the infinite possibilities. Well, the choice that the additional conditions you impose is just up to you. There are 2 commonly used choices, so-called the gate choices. One is del dot A is equal to 0. This is called the Coulomb gauge. Well, it has the advantage that in the Coulomb gauge, the expression of the potential in electrostatics is the same as in electrodynamics. The only difference is that rho is time dependent. So that is the advantage of this Coulomb gauge. So it's trivial to solve phi RT. This is 1 over 4 pi epsilon 0 rho r prime t divided by r minus r prime, t cubed r prime. So the t appearing over here is the same t appearing over there. Well, of course, conceptually this has some issues in the sense that if you change rho at a given point, it changes the potential at other points at the same time, because these 2 times are the same. But that's not really an issue, because we know that the phi is not really the physical thing. What we actually measure is the electric field. And if you make some change, even in this gauge, even if you make a small change at this point, the electric field at some other point is affected after a finite amount of time. Now, this is one of the gauges that this is the gauge, in fact, that we use in magnetostatics also. Now, another gauge that will be using quite often is this one, mu epsilon del phi by del t is equal to 0. This is called the Lorentz gauge. And if you note, in static limit, where nothing depends on time explicitly, the Lorentz gauge basically reduces to the Coulomb gauge. In a sense, this Lorentz gauge is the generalization of the Coulomb gauge to electrodynamics. And in this gauge, you see we have 4 Maxwell's equations, 4 of them. By writing the electric and magnetic fields in terms of the vector and scalar potentials, we already solved 2 of them. So what remains is we need to solve the other 2. And the other 2 equations basically give equations on phi and A. And an advantage of this, of the Lorentz gauge, is that the equation for phi and the equation for A, they decouple from each other. So what they satisfy is mu epsilon del squared by del t minus the Laplacian acting on either phi or A. This is equal to, if it is acting on phi, it is minus rho over epsilon. If it is acting on A, no, it's plus rho over epsilon. If it is acting on A, it is minus j over mu, no, j times mu. So these are the equations that we need to solve. Well, this combination of operators, they appear quite often in physics. So it is given a special name. It's called the D'Alembertian. So if you hear this D'Alembertian or see this symbol, this is what you should understand. Well, the definitions sometimes change. Sometimes this is defined as the D'Alembertian operator. Sometimes minus this is defined as the D'Alembertian operator. So this is plus mu j. Now we will see that this D'Alembertian operator is basically nothing but the generalization of the Laplacian to 4 dimensions, space and time. Now our next task is, so what are the solutions, phi and A? So that is where we had left on Friday. Any questions on this gauge transformations, gauge choices, scalar and vector potentials?
Do these two different gauges tell something different about the physicality of the potential?
You see, if you look at these gauges, or those conditions on gauges, basically they are not physical conditions. Those are things that we invent, we just choose. Now, why do we make that choice? Well, basically, we are defining the electric and magnetic fields in terms of the scalar and the vector potentials, but for a given electric and magnetic field, the choice of the scalar and vector potential is infinite. There are infinitely many of them. Now, the question is, if you are studying something, eventually we will be solving differential equations, writing differential equations for phi and A, which we would like to solve for. But you see, the solutions of differential equations are unique most of the time. So we somehow, if we want to achieve some differential equation that phi and A should satisfy, we should add some additional conditions to pick up that unique thing. Just think of it like this. You want somebody in the class to open up the projector. Okay, how many of you can do it? Well, all of you can do it, but only one should go. And then we have to impose some additional constraints. So let us choose the tallest one go. Okay, so that is our gauge condition. So when you add that condition, well, that doesn't really correspond to anything. Any one of you can, by just using the stick over there, you can turn on the projector. But by adding that unique condition, we just pick up one. We can also have said that, okay, the shortest one should do it. That's also viable, that's also possible. So here, if you just use that analogy here, there are many potentials that give the same electric and magnetic fields. Just for the sake of picking one of them, you add some conditions, some additional conditions. It doesn't really matter which condition you choose. There are different conditions you can choose. These are the 2 of the most commonly used ones. If you want, you can just choose your condition such that phi is 0. You can always choose a lambda such that phi is 0. So that would be a nice choice, for example, because it will eliminate one of the unknown functions. There are 4 functions that we need to solve. But by choosing phi is equal to 0, you are eliminating them, one of them, so there are 3 left. But we will see that this Lorentz gauge, at least for our purposes, will be a better choice, because in this gauge we know that it's, you see, in Coulomb gauge, we said that the potential at the charge distribution at this point creates some potential at some other point at the same instant. So kind of, it seems as if information is transferred from here to all the other points instantly. Well, it's not actually the case, because when you calculate the electric and magnetic fields, you see that the changes in the electric and magnetic fields propagate at the speed of light c. But that thing is kind of hidden. It's not apparent that is in the expression for phi. It also will not be apparent in the expression for the vector potential. But when you calculate the electric field, it will be apparent. Now, in this gauge, in the Lorentz gauge, it will be apparent also in the potentials. So it's just, you have your freedom. You can just use it whichever way you like. Well, you see there are 2 conditions already over here. The third one would be to pick phi to 0. That's the 4th condition. There is a 5th condition that I use. That's another condition. That I use in my work for various reasons. I mean, the condition to choose is just arbitrary. The only thing is that you just need to make sure that given any phi and a, can you transform them to other phi and a's that satisfy the condition that you choose? If you cannot, that basically means that you cannot impose that condition.
So hocam rastgele kafamızdan bir condition mı belirleyeceğiz?
As you wish. Whichever one simplifies your life. For example, I said that we can choose phi to be 0. Can I actually make such a choice? So that would mean if, so, okay. So is it possible to impose this condition? Well, how do we test it? Well, given any phi 0, I can always transform it to this one by this lambda function. And is it possible to choose lambda such that this is satisfied? No, you see, phi 0 is not a constant. Phi 0 is a function of r and t. Lambda will also be a function of r and t. Well, let me choose lambda r of t as phi 0, r of t prime dt prime from t0 up to t. Well, I can always evaluate this integral given a phi 0. But this tells me that the derivative of lambda with respect to t is nothing but phi 0 r of t. So phi 0 minus del lambda by del t is equal to 0. So what this proves is I can always choose a gauge in which phi is 0. This is the proof that I can make that choice. Because you might be tempted to use this gauge where phi is 0, but your friend might be tempted to use some other gauge in which phi is non-zero. So if these two potentials correspond to the same electric field, there should be some lambda that satisfies this condition, that transforms one to the other one. And it turns out that the lambda that you should choose is this one. It's just like choosing your coordinate axis. There are infinitely many coordinate axes you choose. You just impose some additional criteria on your axis to determine a unique set of coordinate axes. For example, when you are studying the projectile motion, you say that, okay, let me choose my z-axis to be in the direction of g, or the opposite direction, x-axis to be in the direction of the horizontal, the component of the velocity, initial velocity perpendicular to the g, and then y is fixed by the right-hand rule. Those conditions are the conditions that you choose to be able to determine a unique coordinate axis. But which coordinate axis you choose? Well, who cares? Just use whichever one you like. Nature definitely doesn't care about your choice. And how are the results in different coordinate choices are related? Well, they will be related by rotations. It's just like you might choose one condition to fix your gauge, he might be choosing some other condition to fix the gauge. So your results, on potentials at least, should be related by a gauge transformation.
Bir şey sorabilir miyim? Eğer şimdi doğa bizim seçtiğimiz condition'ları önemsemiyorsa, bulduğumuz sonuçları neden önemsesin?
Well, you see, we are finding the laws of nature. And the laws of nature are these ones. These four Maxwell's equations, those are the laws of nature. It's not because the nature cares about these equations, it just seems that the nature seems to be working following those conditions. Now we have a choice. There's no choice in those four Maxwell's equations. The choice is we are choosing to describe the electric and magnetic fields in terms of the scalar and vector potentials, so that two of these equations are automatically satisfied. That is where we are making a choice. There is no unique choice of phi and A. There are infinitely many phi and A that corresponds to the same E and the B fields. And similarly, for example, Newton's equations, F is equal to m times A. Well, the nature seems to be working in such a way that this law is satisfied all the time. Now, how do you show the force F, or how do you show the acceleration A? Well, you make choices, like you choose a coordinate axis and talk about the components in that coordinate axis. Well, that nature doesn't care. Now we need to solve this equation, mu epsilon del squared by del t squared minus the Laplacian. Now let me use some arbitrary functions. Let us try to solve this equation. Now, because if I can solve that equation, then I know the solutions of everything over here. If I want to calculate phi, instead of F I have phi, instead of G I should just substitute rho over epsilon. If I want the vector potential, I can choose the x, y, or the z components of the vector potential. Then F just becomes the x, y, or the z components of the vector potential, and G becomes the corresponding component of the current. And I will not derive the solution. I will just prove that the solution is this one. So what does this mean? You see, I have my, let's look at phi. There's some charge density over here. This is my rho. And let's say I want to find the scalar potential over here. At the position r at the time t. Now let me look at this point over here. Now anything that happens over here, it takes a finite amount of time to reach that point. So this distance is, let me just say, this is my r prime. This distance is r minus r prime. So the thing that affects this point happens at the point r prime. It should happen at the point r prime at the time t minus r prime over c. And c is just 1 over square root of mu epsilon. Because any signal from here moves at the speed c, and it will take this much amount of time to reach that point. So if I'm looking at the potential at this point at the time t, I should sum over all the influences, all the effects from this point that happened at an earlier time by this much. And that is basically what I'm doing over there. Okay, this is again, I repeat, this is not a derivation. I'm just claiming that that is my solution. Now what I will do is I will just put this in my differential equation and show that it satisfies my differential equation. Well, you see, if you want, c is just a number, it's not the speed of light in vacuum in this part here. I'm just defining c to have that value. If you are doing everything in vacuum, then this mu will be mu 0, epsilon will be epsilon 0, and this will be the speed of light in vacuum. If you are doing this derivation in a medium, in that case, mu will be the magnetic permeability of that medium, epsilon will be the electric permittivity of that medium, and then c will be the speed of light in that medium. No. It's Einstein's special theory of relativity that says that it doesn't say that information moves at the speed of light. Information can move at most at the speed of light. No? I'm just solving that differential equation over there. Of course, in writing that, I am making that as an assumption in a sense. But once I prove that this is a solution of my differential equation, I'm not really using it. In fact, if you have already taken modern physics, you already know what Lorentz transformations are, right? For example, Lorentz derived Lorentz transformations before Einstein. It was not after Einstein. He derived them using the fact that he was looking for the transformations that leave Maxwell's equations invariant. And he just came up with the Lorentz transformation instead of Galilean transformations. So kind of the special theory of relativity, Einstein theory of relativity, is already embedded in Maxwell's equations. So it's not a surprise that the fact that information travels at most at the speed of light is embedded in here. It's already there. Now, if that assumption is wrong, that the information travels at the speed of light c is wrong, then that would just mean that this solution, this expression is not a solution of my differential equation. Then I will need to look for some other differential equation. Now, if you are interested in deriving that result, look, you have probably studied Green's functions, right? In 2010 or 210 or 209. 210. Look for the Green's functions of that differential equation. The easiest way would be just to take the Fourier transform, to solve it in Fourier space, in momentum and energy space, and then go back to position and time space. But rather than doing that, taking that route, your book has taken the route of just stating the result and then proving that it is the solution. Now I will follow your book. But you can actually derive this result. Now let's see. So first, where is the position dependence of that integral? Where are the position dependence of that integral? You see, the position dependence, our dependence, is over here and also over there. That is something we have to pay attention to. There are two position dependencies. The time dependence is only through this factor over there. So if you would write the second time derivative of f, it is just 1 over 4 pi g, let me put double dot, so this g dot r prime t minus r prime over c is actually the derivative of g, partial derivative of g with respect to t prime, r prime, t prime, evaluated at t prime is equal to t minus r prime over c. This is the dot notation that I will be using. Take the derivative of this function g with respect to its second argument, and that is this dot. And then evaluate that derivative, whatever you put over here. Now we need to take the Laplacian. Laplacian of g. Laplacian of f. I will use index notation. I know you don't like it yet. You will love it in your future life. So that's why I will be using it. So this is del I f. Well, you see, r only appears in the combinations of r minus r prime all the time. So let me take the derivatives of r minus r prime. This is equal to derivative with respect to xi of xj minus x prime j squared under the square root. Well, this is nothing but r squared. I take the square root, that gives me r minus r prime. This will be equal to 1 over 2 times twice xj minus xj prime times Kronecker delta ij divided by the square root of that thing. Well, what I did, well, the derivative of the square root is nothing but 1 over 2, just lower the power by 1, so it is the power 1/2. If you lower by 1, it just, the power becomes minus 1/2. That's why I have the square root over here. Then I have to take the derivative of whatever is inside. The derivative of this thing is 2 times this one times the derivative of this one with respect to xi. Well, if I and j, they are different, the derivative is 0. If I and j, they are the same, the derivative is 1. So that's why I have this Kronecker delta ij. But keep in mind, I'm also summing over this quantity j. So this Kronecker delta ij multiply with this one, it just, this Kronecker delta tells me that when I'm summing over j, only the j is equal to I term survives. The other terms are 0. So del I r minus r prime, this is equal to, well, 2's cancel, I have xi minus x prime I divided by r minus r prime. Well, I will use this whenever I need them. This is equal to d cubed r prime g of, well, I'm taking the derivative with respect to the r coordinate. So I can just put it inside my integration because my integration variable is just r prime, not r. R prime t minus r prime over c divided by r minus r prime. Now let me take the derivatives. This is equal to d cubed r prime. I'm taking the derivative with respect to xi once. The second derivative remains. So this will be equal to, well, the derivative of g with respect to r, well, that is just the derivative with respect to the second derivative, second argument of g, but the second argument, the derivative with respect to the second argument, I just use this dot notation, or let me just give this a name, tr. It's called the retarded time. Retarded because the effects take some time to reach the final point. tr times the derivative of tr with respect to r. Well, that will just give me minus 1 over c times xi minus xj, xi minus x prime I. Divided by r minus r prime. Times 1 over r minus r prime. So this is the derivative of g, all of this thing, multiplied by 1 over r minus r prime. Now I will take the g, multiply it with derivative of 1 over r minus r prime, plus g times del I of 1 over r minus r prime. Well, this was the first step. Now I need to take its derivative once more.
Hocam bir şey sorabilir miyim? Burada şimdi pozisyona göre türevini alıyoruz ama içeride şu şeyi yazdık. G-dat'ı yazdık.
You see, the position is r is only in the second argument. So if I want to take the derivative with respect to the position r, I first need to take the derivative of g with respect to its second argument and take the derivative of the second argument with respect to r. But the derivative of g with respect to the second argument, well, the second argument is time coordinate. That is why I have this dot. This dot over here tells me that I'm taking the derivative with respect to all of the second argument. I'm just using the chain rule here. Let me just try to simplify it slightly. This is equal to d cubed r prime. No, okay, no, let me not simplify it. Let us take the other derivative. This one. Well, we have the same thing. First, the derivative of that one. The derivative of that one just gives me g double dot
r tr times minus 1 over c xi minus xi prime over r minus r prime. There is another factor. Well, okay. When we are taking the second derivative of this one with respect to xi, I get the second derivative with respect to the second argument multiplied by this factor, because this is nothing but the derivative of tr with respect to xi. But I already have one factor. Now I get the second factor, so that's why I have this square over here. And then I have this term. No, sorry. Now I have g dot RTR minus 1 over c del over del xi of xi minus x prime I over r minus r prime squared. Now what I'm doing is I first took the derivative of g dot, multiply by the remaining. Then I have g dot multiplied by the derivative with respect to xi of the remaining terms. And so that is the first one. Now I have the second expression over there. Plus, well, if you look at the second line, again I will basically do the same thing. I have the derivative of g first with respect to xi, but the derivative of g with respect to xi will be just g dot multiplied by this factor. Now let me write it out. G dot RTR multiply with minus 1 over c xi minus xi prime divided by r minus r prime del I of 1 over r minus r prime plus g del squared I of 1 over r minus r prime. Are you following? What I did. Okay, so there I have a g dot. I need to take its derivative. Its derivative becomes g double dot times one of these factors. I already have another factor, so that's why I have the square over here, and what is left is 1 over r minus r prime. Then I have the g dot times 1 minus 1 over c times the derivative of whatever remains. This is the derivative of the first line on the screen. Now the second line on the screen, I need to first take the derivative of g. The derivative of g is g dot multiplied by this whole expression over here. And then the second term is just derivative with respect to xi of 1 over r minus r prime. Then I have the g multiplied by the derivative of the second term. It is this one. Now I will make some simplifications. Do you recognize this one? So del I squared 1 over r minus r prime is just the Laplacian of 1 over r minus r prime. What is the Laplacian of 1 over r minus r prime? It's the direct. You see, 1 over r minus r prime is nothing but the potential created at the point r
by a point charge at the point r prime. The volume density is just a Dirac delta. This is 4 pi Dirac delta of r minus r prime. So it's kind of trivial to evaluate that integral. So we started with Laplacian acting on f is equal to. Now here we have a Dirac delta. Here we have this Dirac delta. I can just evaluate the r prime integral. Keep in mind that G has the arguments r prime and tr. So this is equal to G of r, t. Remember and keep in mind that tr is equal to t minus r prime over c. Now this Dirac delta tells me that when I'm evaluating this r prime integral, the only thing I need to do is wherever I see an r prime, I should put an r. If in tr you put r instead of r prime, t retarded time is just t. Well, this is one part that we were looking for in our solution. This is this term. Now let's try to do a bit more simplifications. Let's go up. Let's look at this term. xi minus xi prime squared. That is nothing but r minus r prime squared. Here I have r minus r prime squared. So they basically cancel each other. So when I take the square, this term and this term cancels each other. When I'm taking the square though. Now here I have minus 1 over c. If I take the square, it just becomes 1 over c squared. Well, 1 over c squared is nothing but mu epsilon. Anyway, I can just take it out of this integration. What remains is just g double dot over r minus r prime integrated. Well, g double prime over r minus r prime integrated, well, I forgot this factor 4 pi, is just the second derivative of f. You see here I have 4 pi's in my original definition. So it cancels this 4 pi. Now this term, the first term just becomes plus mu epsilon del squared f by del t squared. Do you see how I obtained the second time derivative of f? Okay. There is the second time derivative of f. At the top part of the screen. Now let's look here. Do you see how I make this cancellation when I take the squares? xi minus xi prime, the component squared, when I sum over the component, it just gives me the r minus r prime squared. So square of this one is equal to the square of this one, so they cancel each other. I have 1. Here I have 1 over c squared, which I can just take out. What remains is d cubed r prime over 4 pi g double dot r prime at tr, retarded time, divided by r minus r prime. Look at the second derivative of f. So this first line is equal to the second time derivative of f, multiplied with 1 over c squared. And 1 over c squared is nothing but mu epsilon. Now, of course, I still have 2 more terms.
plus 1 over 4 pi d cubed r prime g dot r prime tr times minus 1 over c del over del xi minus xi prime divided by r minus r prime squared plus xi minus xi prime over r minus r prime del over del xi of 1 over r minus r prime.
You see, in these expressions, I already have almost my solution.
Just I need to make one correction to my solution though. Let's see it later on. So what do we have? The Laplacian of Laplacian minus mu epsilon del squared by del t squared acting on f is equal to g.
This was the equation I was trying to solve. Well, I seem to have that additional term if I didn't make a mistake.
Plus 1 over 4 pi d cubed r prime g dot r prime tr minus 1 over c.
Let's take those derivatives. Now, derivative of xi minus xi prime with respect to xi is 3.
Why 3? This is nothing but Kronecker delta II.
But keep in mind, I'm summing over I. So as I'm summing over I, Kronecker delta I is 1. There are 3 possible values of I,
So this is equal to 3. That's why I have that 3 over there. Plus xi minus xi prime times minus 2 derivative of minus 2 over, let's say, r minus r prime cube times the derivative of r minus r prime with respect to xi, and we had already calculated it to be xi minus xi prime over r minus r prime.
that is the derivative of the first term. Well, we can even make more simplifications. This times this is r minus r prime squared. Here I have a cube, so basically this times this divided by these is 1 over r minus r prime squared. I have minus 2, so it cancels 2 of them.
Well, so what I will have is this and this multiplied cancel this, and this becomes 2. And minus 2 divided by r minus r prime squared cancels 2 of these, so I end up having 1 of them.
So this is the first term.
Now let's look at the second term. The second term is minus xi minus xi prime over r minus r prime. Well, that derivative is now plus minus 1 divided by r minus r prime squared let me write it explicitly. Plus xi minus xi prime divided by r minus r prime That derivative is minus 1 over r minus r prime squared multiplied with xi minus xi prime divided by r minus r prime. But you see again, this times this cancels these two, and so this cancels this one. So that term is 0. And we end up having minus mu epsilon del squared by del t squared. F is equal to G. Where, let me rewrite it, Fr of t, this is equal to integral d cubed r prime divided by 4 pi g of r prime tr divided by r minus r prime.
Well, this is not the equation I started with. In the equation I started with, these were reversed, but it's just instead of g, put minus g.
Let me just add the minus sign over here, so everything you wrote afterwards is correct.
Nereye koyduk?
You see, that is the equation I want to drive. I want to solve.
And the f that I define in this form
Is a solution of this equation. Okay, so if you couldn't follow the derivation, if you want to follow the derivations, you should do it on your own. But basically, these are the steps. Now, I know it's boring, but it's kind of one of those things that's boring, but you need to do it once in your lifetime at least. So now we know the solutions. For again, general F and general charge density and the current density, we can straight away write the potentials. And that was what we were trying to achieve.
So that tells me that phi at the point r and at the time r and t is equal to 1 over 4 pi epsilon d cubed r prime rho of r minus, no, rho of r prime at the retarded time divided by r minus r prime, and a, this is equal to d cubed r prime mu over 4 pi times j r at the retarded time divided, no, this is r prime, r minus r prime.
Well, the nice thing about this Lorentz gauge that we are using is, in fact, if you just remember our discussions in electrostatics and magnetostatics, these are identically the same expressions that we wrote for potential and the vector, scalar potential and the vector potential in the case of electrostatics and magnetostatics. They have exactly the same form. The only difference is that here, since we are looking at the time-dependent case in electrodynamics now, the time here is the retarded time. That is the only difference between our expressions in electrostatics and magnetostatics. Okay, let's give a 10-minute break now. So wake up, and then if you have questions, we can continue at the beginning of the next hour.